we start. So, what is the date today? So, 9/02/2024. Okay. So, yesterday we talked about RNNs and how do we draw them. So, let me just try to draw this architecture now. So, we talked about RNNs. If this is the black box, so if let us say this is the black box, what are we entering over here? It is x, t, then it receives from here the previous timestamp at minus 1, it passes at, and if you want to take an output, that can be y hat t, right? How are these guys connected now? Let us try to see the internal structure. What were the equations? That will help us get here. So, these were the equations. X and A are related, right? So, right. So, we see WAX here, we see WAA here, right? So, here we see WAA, and then we add both these. We add WAX. So, this is WAX times XT plus, so this is basically a plus here, okay, addition, and then what do? This summation goes to, so I am not drawing B's here, this summation goes to here. What is this going to give me? So, this passes through a 10H, this passes through a 10H, and right hand side it goes as AT. Our AT is, so why I am doing 10H? Because I am saying G1 is 10H, okay, 10 hyperbolic. Now, so AT is done, that I have passed, and on the right hand side, so and this goes up if you want to compute. So, let me try to zoom it. Okay, this is how it looks like. This plus is something I don't like, so plus, and then this summation, we basically take 10H of this, you output AT, and if you want to have an output here, this is what you do. So, is this picture clear? Right. Now, I'll so see, before I talk about how to train this and everything, I am going to talk about one more architecture. So, we talk about that architecture first, and then maybe starting next week, we will talk about more theory. So, it turns out that nobody uses this architecture. So, these are called plain or vanilla RNNs. They have some problem that we will talk about in the coming week. So, right now the point of interest to us is, even though it looked like it will capture the sequence and will be able to learn how to, so it does learn how to output next word, but is not very efficient at some things. Okay. So eventually people end up devising new things. So this is plain vanilla RNN. For some reasons does not work. We'll talk about what are those reasons. But so we'll take these two architectures side by side now. What is the another one that I'm going to do today? Anybody knows? So we'll do LSTM today now. Okay. This is plain vanilla RNN. LSTMs are also RNNs, right? But they don't suffer from the problem that this guy suffers from. Okay. What is that problem? We'll take up for both these architectures later. So I want to draw LSTM now. And I want to keep comparing. So let me try. Input is xt, that is going to be there. So input is xt, what else? What else? We want it to receive 80 minus 1. Okay. What more? It turns out, so let me try to make this big and I hope this will be sufficient. So you are having 80 minus 1 xt and you take out 80 and there are a lot more things inside. Okay. So first thing, so this xt comes here and 80 minus 1 comes here, so maybe only until here, comes here, okay, and then it passes through something called forget gate. Okay. And then the same thing. So let me write it this way, in fact, that this xt we are short circuiting over here. So everywhere xt is there, you can't get rid of xt. Okay. So xt is there everywhere. Now there is yet another gate called update gate. Okay. Yet another thing called h and one more gate called output gate. And I will have to shift this 80 a bit up. So somewhere here we have a t. Okay. This goes up here. So there is yet another quantity in LSTMs called C of t minus 1. You take this C of t minus 1, do an element wise multiplication, So update gate goes up. So this is not a circle, this is a star again, okay, and plus out goes CT okay, and 10H okay. So this becomes CT of course. So this is how an LSTM looks like. So what is actually used is not this simple architecture, but a much more sophisticated architecture, this one. Okay. Why do we do this? Why LSTMs and not RNNs? I have not answered this. Anybody knows? So RNNs suffer from, okay. No. So is this fine with everyone? How do we write equations for it now? So let me just try to. How do we write equations for it? Maybe what I'll do is this one and we'll try to write them down here. Batao. So LSTMs, this architecture was proposed in 1997. Back then deep learning was not at all a hot topic to work on. Those people who were working, they were working purely because of their interest, right? The two authors, two German people, I think German, Austrian, somewhere around that people. So when they came up with this architecture, so one was the master students, another was the professor. They moved on to other fields because fine, master thesis was done and everything was over. And then suddenly in 2012, 2013, 2014, this paper starts getting citations like anything, because plain RNNs don't work, but this architecture works. So this is a classic example of a paper which initially was lying dormant, right, but then suddenly starts getting attraction. So what are the common things that we have in plain RNN architecture? What are the common things here? Yes. What was the equation for RNN? See, it was WAX. So WAX was sitting here. Now for those who came late, xt, this we have short circuited to everyone. So everybody is receiving input xt. Okay. Now, so and also 80 minus 1, so is 80 minus 1, yes. Yes. So what was RNN? What should I get rid of to get back my RNN? The plain vanilla RNNs. So first of all, I should get rid of this C, right? This was not there at all. Forget update and output were not there at all. C tilde t was not there. So xt 80 minus 1 goes through 10h. This is our first equation. Okay. See, this is our first equation, this one. This one. So x gets multiplied with WAX, 80 minus 1 gets multiplied with WAA, and then you take, so G1 is basically 10H, that's what we are saying, okay, and we come back here. Right. So this is our output, so y hat here, not y. So plain RNNs were remove this, remove this, remove this, remove these, everything else, xt 80 minus 1, 10h, and simply, so whatever comes after 10h, send that back as 80, send that up, and then which weight matrix do you multiply with? WYA, take softmax, and you get your y hat. Okay. Now this has a lot more things. Why this is a question that we are still keeping open. Okay. So what should be my first equation? My first equation could simply be WAX times what? XT actually you could combine these two, but in the interest of time I am not doing that part, so let us continue with what we were doing. WAA, you can combine these two things, you can concatenate these two vectors and you can concatenate these two matrices to basically talk about just one vector and one parameter matrix. So A t minus 1 plus BA, right? Now I need more space. But I want to keep this figure also. So we have this equation, and this equation was for what? If you put 10h here, we are talking about what lies here, right? So we want to see what lies here, what lies here, and what lies here. So all these, they are doing same thing, this kind of thing, and you take you take 10h of this, and let's say you, what do you get? C tilde t, so you get C tilde t. Is this thing fine? This is same as what we were doing in case of vanilla RNNs. So in case of vanilla RNNs, this C tilde t was same as 80, and now you pass this 80 up, multiply it with W by A, take softmax, and you get the probability distribution. Fine? I see some blank faces, which is fine because so much is going on here. Anything? Okay. So this is what you have. Now, so since we are calling them gate, so this is again notation from Andrew Ng, deep learning specialization, or maybe you can go to CS 230 Stanford. So this is our, so let us try to be in the order now. So the first gate is forget gate. Now let's say update. Let us do it the way he is doing it. Now, so forget gate is, what is this guy doing? Analogous to this. W. So what we are calling this is, since we are talking about update, we are saying WU takes input xt 80 minus 1 plus bu. Okay. I'm coming to everything. Okay. So what is this guy now? I want you to see a similarity here. See what I would have done. There's a step which you can fill in. See what is xt? So let me just quickly do it here. See, this is WAX gets multiplied with xt. Okay. So this gets multiplied with xt. Now what else is going on? WAA gets multiplied with 80 minus 1. Okay. Now what are the dimensions of WAX? So this was 100 cross 300. So 100 cross 300, and this was 300 cross 1, and this was 100 cross 100, and this was 100 cross 1. What is the output here? 100 cross 1. Output here is 100 cross 1. So we can basically, now let's say if I do WAX here, and so now I think it thick ho gaya hai, XT here, right? So WAX, this matrix here, will get multiplied with this one. This is 300, and remaining 100 I keep 80 minus 1. Okay. Where should I put my WAA? So what is this guy? 100 cross 300. So that means rows are 100. So I can fix my WAA here. So just concatenate this and concatenate this. Now WAX will get multiplied with only XT, and WAA will get multiplied with only 80 minus 1. And finally what you get is a sum of the sum that we were doing. Everybody is with me in here? Simple matrix manipulations, nothing else. Okay. So now this whole thing is what they are calling Oops. WU, right. So this whole thing they are calling WU. Right. So this WU, so this guy is nothing but a concatenation of xt and at minus 1, and similarly we could have done here as well, and this is how they are writing in those equations. Okay. So now is this equation same as this one? What is the difference then? Is this equation same as this? Yes. What is the difference? So here they take sigma. ये क्या है यार? So I think it was thick. Okay. Okay. Right. So what is the difference now? What are the differences here? Now, so now let me just rewrite this whole thing like this. It was 10H and then W C X T A T minus 1 and plus. Okay, so now we are not using A here, we are rather using C. Right. Done? So these two are same things I am repeating. Now, what is this guy? You should be able to give me this now. See here, you should be able to give me this now. So this is W F X T A T minus 1 plus B F and then sigma. What more? So tau O, that becomes WO XT sigma. My question remains the same. What is the difference with plain RNNs? By difference I mean in terms of parameters. Which one has more parameters? So given any RNN, can you compute the number of parameters there? What will be the number of parameters? WAX plus WAA plus WYA and plus these two biases, okay, BA and BY. So you know the number of parameters, you can compute the number of parameters in a vanilla RNN exactly. Now what is going on here? So what is the difference between these equations that we have written and the equation that we had written for RNNs? LSTM is also an RNN, so we call those things as plain or vanilla RNNs. Yes. More parameters, but how many times more? What are the dimensions? So my question, so to be precise, what I want to ask is, what are the dimensions of WC, WU, WF, W0, sorry, WO? Do this math and tell me what are the dimensions of WC, WU, WF, WO. And assuming ki we are talking about number of neurons in hidden layers are 100, our word embedding size is 300. Yeah, that's all you require. Okay, let me write a few more equations. This one is okay with everyone? I don't want to keep it now. Or maybe we can shift it. Okay, we can just put it here somewhere. Talk about that later.
सर ये WC के अंदर जो WAX और WA आ रहे हैं उन दोनों को मिला के होता है?
Just a second. हाँ.
सर WC के अंदर जो WAX और WA आ रहा है उन दोनों का मिला के होता है?
Exactly. So now see this WU, see here we were talking about WAX and WAA. So what is the second subscript in both X and A? Now we are saying X and A are captured here, and this WU is one bulky matrix that operates on both. So this WU has same parameters as WC. WC has same parameters as WAX plus WAA, plus in the sense concatenated. Okay. So this guy was 300 cross 100. This guy was 100 cross. Right.
WA हो गया 100 cross 100.
Right.
तो 100 cross 400.
Right. So 100 cross 400. This guy is 100 cross 400. 100 cross and 100 cross 400. Okay. So what else? So let me shorten. No, we are not yet done. So this was just xt. Now what is left, by the way? See, we have talked about this computation, we have talked about this computation, this one and this one. A few more equations are left. To be particular, what is left? We have not yet written what is, what goes out, we have not yet written. So what is CT and what is AT? So CT is now we are done with all the equations of LSTM. Of course, except output, because output is still going to be You take softmax. Okay, because why softmax? Because we are specifically talking about one application called language modeling, right? If you want to do something else, you won't. So let's say if you were doing reviews, so where text is converted into 5 stars, so in that case your softmax will be of size just 5. Okay. Okay, so we are here. Tell me which equations, which part are we talking about? So you have tau u, tau f, tau naught here, c tilde here, all these 4. Okay. So c tilde and tau u, c tilde and tau u. Okay. You take element wise multiplication plus tau f, this is tau f, you take element wise multiplication with ct minus 1. You add both of them, so you add this part, so you take element wise multiplication here, it is not a dot product, it is element wise multiplication here, element wise multiplication here, add both these vectors and get a new ct. Now this ct just goes away. Okay. What about at? At is here. You take ct and 10h is missing here. Okay. So okay. H. So this part is coming from ct and tau o is coming from here. What is this sign? Element wise multiplication, and that becomes your at. This bulky architecture is what was being used in almost every sequence to sequence problem until 2017. Okay. And since 2017 transformers came up, they slowly, in fact not slowly, they very rapidly replaced LSTMs. Attention is all you need. Yes. Okay. So my questions, sir. Any questions you have in this? All we have talked about is just architecture, how are things connected. We have not tried to understand any damn thing here. We are just seeing how things are connected, what are the parameter matrices, where are the parameter matrices, and that's it. So if I ask you the number of parameters in this LSTM, can you tell me what is it? Yes. Do you have any parameters here? So there are no parameters here. Okay, these two equations, they don't have any parameters. All parameters are lying in these 4 equations, and they are all same. Okay, so tell me, in our setup, what is the dimension of c tilde t? What are the dimensions of c tilde t? कुछ कह रहे थे? $100 cross 1? Right. So it is 100 cross 1. Why so? This will give me 100 cross 1 plus 100 cross 1. This was 100. So this whole thing is 100 cross 1. 10H will operate element wise. So this remains 100 cross 1. So keep writing. So this guy is 100 cross 1. So let me not make your life simple by writing it here. Okay, I will write it in the end. Now tell me, what is the dimension of tau u? 100 cross 1, nothing changes, everything is same. So what has changed? If nothing changes, why do I have this as two equations? So activation function has changed, but that is immaterial. What has actually changed is weight matrices. All these weight matrices are different, they are learning different parameters. Write this down. Okay? They are all learning different parameters. Is WU same as WC or WF? WC is different from WU is different from WF, and three of them are different from. So all these are four different parameter matrices. What are the dimensions of tau F? 100 cross 1, tau O 100 cross 1. Everybody agrees? What is the dimension of WF? It will have elements like this. So WFX times XT plus, let's call WFA times AT minus 1. So all these, not this one, but this WC, WU, WF, WO, they are all 400 cross 100 in R settings. Okay? And what are R settings? Where is this number 400 coming from? 300 is the length of my XT and 100 is my length of AT. Okay? So, fine, done with this. Tell me next. So, what is the dimension of this thing? This whole thing? Tau u element wise multiplied with C tilde T. 100 cross 1, because both these vectors are 100 cross 1, 100 cross 1. You are not taking dot product. If you were to take dot product, what will be the size of the resulting thing? It will be a scalar 1 cross 1. But you are taking element wise multiplication. So first element gets multiplied with first element, second element gets multiplied with second element. This is not a matrix multiplication. This is a element wise multiplication. Okay, so let me write it here. Okay. Tell me what are the dimensions of these two guys. What is CT minus 1? Right? So CT minus 1 has dimensions same as CT, and we have already seen this guy must be 100 cross 1. So this whole thing has to be 100 cross 1 and this thing has to be 100. So this is 100 cross 1. This is normal matrix addition. Tau f is 100 cross 1. What must CT minus 1 be? 100 cross 1, and hence CT is also 100 cross 1. What is CT? 10H. This whole thing is 100 cross 1. This is 100 cross 1. Element wise multiplication 80 gives me. So is this whole structure clear now? So you are basically getting two vectors input from the previous timestamp. Both are of size 100 cross 1, or they both are of same size if you don't want to take the number of hidden layers. So where is this 100 coming from? Number of neurons in the hidden layer. Okay. So these two will be same, outgoing will be same as incoming. What are the dimensions of XT? 300 cross 1. Where is this 300 cross 1 coming from? We are saying our word embedding size is 300 cross 1. This is what it is. Okay. Now, one more equation is left, and that you can tell me. So, output is a function of what? CT or AT? Look at this figure. Output is a function of CT or AT? See, right. So, it is everything else is, everything else is captured by AT. If you see, this AT is receiving input from everyone. Forget, update, 10H, output, everything has something to say here, right? So, AT, if you are doing language modeling, what do? Which we are doing in our case. So, what should my YT be now? So, what I end up doing is Y hat T is softmax, W YA AT plus maybe plus maybe B Y. This is LSTM. So good that we managed to fit everything in just one board. Yes. Are you okay with how things are connected? This is all we have done in this class. Right. Okay. The most important part, when you are writing programs, when you are testing your hypothesis in deep learning, the most important thing is to know your matrices. Where are they? What are their dimensions? More than 75% of your bugs will be coming from there. Okay. So given that you understand how are these metrics interconnected, whether they are the same or not, which operation is going on, this is all we have talked about. We have not talked about whys of anything at all. Alright, so done for today.